Okay, our speaker today is Rolly Pereira. Rolly is from ICCS and he's working there as a researcher in programming languages. And he was at Alan Turing Institute before and he's going to talk to us about open computation. So thanks so much for coming. We look forward to the talk.
Hi, everybody. Thanks for having me and thanks, Keshav, for the invitation. So, yeah, as Keshav said, I'm a postdoc. I started at the ICCS in September, working with Dominic. And I'm going to talk today about how developments in programming languages present an opportunity to really enrich what we mean by the open science. So this is a topic I've been working on for about 10 years with colleagues at Bristol and the Turing and elsewhere. And I'm hoping to tap into a lot of your expertise over the next 5 years or so. So I thought this would be a good opportunity to introduce myself, introduce the topic, and say something about how I see it moving forward over that time frame. So the talk's going to be split into two halves. The first half is a bit more PL oriented, but it won't be too heavy. And then in the second part, I'll kind of sort of contextualize it into the kind of climate science setting that. So to kind of frame the problem I'm in, let's think about what we actually mean by the open science. So when we think of open science, we usually think of open source, open data, perhaps working in open and transparent ways, but what else? So this Royal Society white paper does a good job of making it clear that these are really only the ingredients of open science. The actual goals of open science are ergonomic. We want data and the outcomes derived from data to be accessible, we want them to be intelligible, and we want them to be easy to evaluate and reuse. So these are the goals that these ingredients are sort of intended to facilitate. So if these are the goals of open science, what's the actual user experience today? So here's some science. It's open science. That means I can go to GitHub, Zenodo. I can pull down some source code and a data set. And if I've got somewhere between a couple of hours and a couple of days, I might be able to reproduce these charts on the left. But if I actually want to understand how these artifacts are related, if I want to understand how the code and data actually contributed to these artifacts, then I'm going to need a much more substantial investment of effort. And the problem here is, I think, that the computational pipeline that's used to produce these outputs is just too ephemeral. So by the time I'm looking at this PDF, all I have is a bunch of pixels on the screen. And if I want to reverse engineer the complex relationships between these outputs and these raw materials, that's a non-trivial undertaking. And that's going to be true even for the authors of the paper. So, okay, so we can and clearly should keep improving open science practices, but that doesn't directly speak to this issue of how to make open source and open data more intelligent. So I think of the problem as really to do with the computational process itself. It's simply too monolithic, too ephemeral, and too closed to support these kind of ergonomic needs to make research outputs intelligible. So the kind of research question that preoccupies me is, can we use techniques from programming languages to help us rethink this picture? Okay, so I'm going to talk a bit now about work I've done sort of over the last few years towards this goal, and then I'll talk about some of the research that we're planning to do at the ICCS. So the basic approach that I've taken is quite simple. So the idea is really, rather than throwing away the information about how inputs and outputs are related, we're going to retain it. And then we're going to make it available to the user by enriching outputs with additional interactions. So we're going to kind of give up on this idea of execution as something that's ephemeral and whose only job is to produce a result. And we're going to instead think of it as a relationship between inputs and outputs, a relationship that's both persistent and fine-grained. And what I mean by persistent is that outputs are going to be equipped with an execution record or a trace, which explains how they were computed. And then the fine-grained part means that we're going to use the information in that trace to allow the user to explore the relationship between specific parts of the inputs and code, how they relate to specific parts of the output. So this isn't a new idea. This is something called dynamic program slicing. It's an idea that dates back to the 1980s. And in my PhD, my contribution to this line of work was a particular a way of setting this idea up where these two different sort of directions, these two different ways that we can reason about the relationship between inputs and outputs are characterized by a pair of operators, these left and right triangles, that form a Galois connection. So a Galois connection is just a pair of functions that are near reciprocals of each other. They're each other's closest approximation to a reciprocal in some sense. But I'm not going to say anything more about Galois connections here. All we need to know is that they're a good fit for this problem because they have a natural interpretation in terms of resource utilization. So we can think of this left triangle operator as a way of saying, we care about what inputs do we need in order to calculate those outputs. So it's a kind of demand operator. And then the right triangle says what output can we make given only a set of particular inputs. So it's a notion of sufficiency. So the idea then is to take this kind of metadata about your computation and bake it into the artifact itself so that the artifacts become more kind of transparent and self-explanatory. And we're no longer requiring the user to download a repository and try and reverse engineer all this information for themselves.
Did you want this at the end?
Yeah, I think that would be good. Thanks. Okay, so let me show you what this looks like in our current kind of prototype. So this is a project website where we've got some interactive demos or interactive visualizations. So these are charts showing some renewable energy data. And the program for the charts is fairly standard functional programming code. So this is an untyped language. You have to forgive the formatting here, it's a little bit awry, but apart from that, it's a very standard functional programming language with higher order functions and list comprehensions and so forth. So the code for the charts can be expressed using these bits of code. There's a data set as well. And then what this programming language fluid does is automatically enrich the outputs with additional interactions that allows me to explore the relationship to data. So for example, if I click on this point here, then I can see that these two data values were needed. And that's because in order to compute the y coordinate of this point, we have to divide these two numbers. Now, we're not able to sort of show the fact that it's a division operator that was applied to these numbers, and that's why they were needed. But already you can see that it's sort of revealing some useful information about the computation. If I select another point, I can see that more data is needed. Whereas if I select the this Germany bar on the left, for example, then I see a different view of the underlying data set. And in this case, the height of the bar has been computed by adding these four numbers together. So this is what they call extensional transparency. It doesn't say anything about kind of how these relationships come about. It just says what the relationships are. So it's future work to kind of, if you like, enrich that with intentional information so that I could have the user interface be able to explain to me that the height of this bar is actually the sum of these four numbers. But even with this kind of naive implementation, we can already see in this case that we're looking only at data for 2015, which isn't apparent from the legend, for example. So the key takeaway here is that the programmer hasn't had to kind of code up any of this stuff themselves. They've just written the program, and all this kind of infrastructure is being provided by the programming language itself. So you could, of course, go and program something like this yourself, but it'd be quite a big undertaking. And perhaps more importantly, you'd end up with a very different kind of program because you'd have to not only have a load of GUI code into your program, but you'd have to somehow take your knowledge of the data dependencies that arise in your analysis and kind of embed those back into the program. And you'd end up with something that's quite brittle and unreliable. Okay. So I'm going to take a bit of a technical detour now into some later work. So this doesn't really speak to the bigger picture that I mentioned at the beginning, but it's a useful bit of background because it shows that this idea extends to from kind of toy languages to more realistic features like side effects and concurrency. So I'm just going to spend a bit of time on the concurrent aspect of it because it's relevant to what I'm working at the moment. So this approach, which we call Galois slicing, is a dynamic technique. And that means that these slicing operators are defined for a particular execution. So in a concurrent language where you have non-determinism, the kind of question that arises is what are the specific executions with respect to which you're going to define these operators. So the way we approached this was to appeal to a standard distinction between two different kinds of non-determinism. So the first kind is when the non-deterministic choice can have a kind of impact on the actual outcome of the computation. So for example, if there are two different customers that I could interact with in order to sell a product, then the choice of who to interact with obviously has observable consequences. And we can contrast that with another kind of non-determinism when there are just two independent steps. So we might have two processes running in parallel, either of them can take a step, and it doesn't matter which order we take them in, whichever interleaving we pick, we're going to end up in the same state. So we call that unobservable non-determinism. And our result in this paper, and then using this distinction, you can define a notion of equivalence, sometimes called causal equivalence, which just says the two executions are equivalent if they differ only in these unobservable choices. And then what we showed in this paper is that we defined a slicing algorithm for concurrent programs and then showed that slicing with respect to two causally equivalent executions always produces the same result. So what that means is that, if you like, the notion of specific execution that's appropriate to slicing in concurrent languages is the idea of a causal equivalence class. And a practical upshot is that you can implement slicing concurrently using any representative view of the equivalence class, in other words, any interleaving, and get the same result. Okay, so that's the kind of most technical part of the talk out of the way. So let me circle back now to the kind of bigger picture. So I've talked about relationships between inputs and outputs, sort of fine-grained relationships, and how we might bake those into outputs to make them more intelligible. But what else can we do to make outputs more intrinsically intelligible? So one thing we know from geospatial applications like Geoda is that something called brushing and linking can be a really valuable comprehension aid. So this is where I make a selection in one view and related elements in other views are automatically selected. So this is a very important feature, but it's poorly understood. It's not always consistently implemented, and there's no real formal understanding of what it means for two outputs to be kind of linked in this way. So our insight in this work is that we can think of two outputs as related in this sense when they compete for inputs. So in other words, when their demands overlap. So we can compute the demand associated with a set of outputs X using this left triangle operator. But it's not easy to find the other outputs that overlap with the demand associated with X using just the left triangle. It kind of points in the wrong direction, if you like.
So do you mean intersect there? What's the set operation between X and Y?
So it would be sort of non-empty intersection.
Yeah.
So the left operator is hard to count. We want to ask the question in the other direction. So given the demand associated with X, we want to find all the other outputs that need anything that X needs. So we can't answer that question using the left triangle, points in the wrong direction. So you might wonder what can't be used the sort of right triangle that I mentioned earlier, because at least it points in the right direction. So the problem there is just that it answers the wrong question. It says, of a set of inputs, what are they sufficient for? So in other words, what outputs, find me all the outputs whose demand lies within the set of inputs, rather than find me all the outputs whose demand intersects in a non-empty way with a particular set of inputs. So what we showed in this work is that we can compute the outputs which have overlapping demand if we enrich our notion of slice to support negation. So in our previous work, the notion of slice was essentially a value with holes. So the holes represented the unselected parts. There was no notion of complement, and the slices of a particular value formed a lattice. So in this new setup, a slice is just an arbitrary subset of paths in a value. There is a notion of complement, and the slices of a particular value now form a Boolean lattice. So what that means is these left and right triangle operators for reasoning about relationships between inputs and outputs now have dual jewels. So we can use that to calculate the related outputs. So suppose we have two outputs, B and C, and we want to know for some particular part of C, what are the parts of B that have overlapping demand. Well, we can do this by going this way through the diagram. First of all, we say what are the inputs needed for this part of the output, and then we can use the De Morgan dual of the sufficient for operator to find all the parts of B for which these inputs are necessary. And that tells us exactly the parts of B that overlap with the kind of, whose demand overlaps with the incoming demand from C. So I'll show you what that looks like in our computation. So if instead of setting Germany on the left, I were to select USA, then I see that all the 2015 points are on the right highlighted. And that's because each of these points is consuming some of the data needed to calculate the height of the bar on the left. So each point is actually just consuming one of these data elements here. And if I select China instead, then I'll see something similar because again, each of the points on the right needs one of these data elements used for the bar on the left. Whereas if I select Germany on its own, then I'll see no points highlighted on the right, and that's because none of the Germany data is being used on the right at all. On the other hand, if I select one of the 2015 points on the right, then I'll see that both of the bars, the China and USA bars, are highlighted on the left. And that's because each of these bars needs at least one of the points needed to calculate this point on the right. So it would be useful here if we could kind of show the overlapping demand. So you can imagine a kind of richer interaction where if I move my mouse over China in this situation, it would apply slightly darker highlighting to this cell to show you exactly where the demand is overlapping the data set. But the key point here again is that the programmer hasn't had to kind of implement any of this stuff themselves. It's kind of baked in. And so we can turn this really useful feature, brushing and linking, which is a bit kind of ad hoc today, and make it something more robust and something potentially ubiquitous. And also in this setup, there's always some mediating data that explains why two particular outputs are linked. So in this case, these cells at the bottom explain exactly why this highlighting arises when we make these selections. Okay, so I'm going to talk now about something we're currently working on that builds on the concurrency stuff I mentioned earlier. So one problem with this approach is performance. So we spend a lot of time rewinding and replaying sequential traces. And that doesn't really make sense because the reason slicing is useful in the first place is because even ostensibly sequential programs have lots of independent parts. So we can take advantage of this by turning to another well-established technique in the literature called dynamic dependence graphs. And a dynamic dependence graph represents just the causal structure of the program. So in other words, information about what depends on what. And if we use that as the execution record instead of a trace, then we can define our bidirectional operators over the graph now instead of the trace. And if we think about this example I showed you earlier, because the bars here are independent, and as are the points, we can actually compute the overlapping demand just by chasing a few edges in the dependence graph, rather than rewinding or replaying the whole computation. So this is kind of early stage work, but we've already shown like a 300 times speed up in cases with a lot of parallelism, like array convolution, and even in kind of non-parallel cases, we're seeing that it's a lot faster than the old approach. And the mathematics gets kind of simpler as well, because the operators are now no longer dependent on any particular details of the language they're just defined over the graph. For example, given a procedure for computing the backwards analysis over the graph, we can derive an efficient procedure for computing the forwards analysis, because the forwards analysis over G is just the De Morgan dual of the backwards analysis over the opposite graph. And in the theory of Galois connections, we know that the upper and lower adjoints determine each other, but not in a way that suggests any kind of efficient implementation. So this is still a useful back to know.
Just a quick point of clarification.
Yeah.
Asymptotically faster than what? So faster than not having the data dependency graph, but doing a sequential isolation.
Yeah, so faster than using the kind of the previous approach, which was a trace. With a trace, we have to kind of rewind all the steps.
Okay, I see. So you're saying, right. So this is including the asymptotic complexity of generating the DDG in the first place.
No, that's just the actual slicing part. It's a separate kind of data. Yeah. So what we're trying to do here is make the interactions very fast. So there's a sort of one-off cost you pay, which is building the DDG, but it is actually comparable. Building the trace and building the DDG sort of takes similar time. Okay, so yeah, so this approach is kind of looks promising, but it's kind of early days. But hopefully, it can be a foundation to move this work forward over the next few years. So that brings me to the next part of the talk. So I want to talk a bit about kind of what this sort of computational transparency might look like in a bigger context in climate science and computing for climate science. So what does computing for climate science actually look like? So this is my outsider's view of it so far. So feel free to correct me on with this. So on the one hand, we have climate models. So climate models are not single models; they're actually coupled collections of coupled models of various aspects of the Earth system, sea ice, hydrology, and so on. And then they're usually integrated with an online process of data assimilation. So that's when you're synchronizing the model with observation of data, and then this kind of whole composite system is essentially a digital twin of the Earth's climate. So that's climate models, but we also have all the things we do with climate models. So we have all the kind of science we do on top of climate models. We have ecology, biodiversity, and so on. And we have human concerns like water security, and food security, and so on. And then all the science communication that goes along with that. So publishing, journalism, education. And computing is essential to this part of the picture as well. But we're not just doing the upper tier to satisfy curiosity. We're also trying to close the action perception loop. We want to influence public opinion, public policy, and ultimately the trajectory of this kind of Earth system that we're part of and doing a very bad job of steering in any kind of sensible direction at the moment. So the kind of transparent programming languages I've been talking about have potential, I think, to improve things like peer review, make it easier to reproduce and reuse other people's work, to give us better diagnostics and so on. But we don't just want science to be faster, we want it to be fairer and more inclusive as well. And I think automated correct by construction transparency has potentially a kind of valuable role to play there as well in making science more kind of accessible and more robust in the presence of misinformation and so on. So the value proposition, if you like, of this kind of pervasive transparency isn't controversial. But I think it is equally clear that it's not going to be easy to achieve in the kind of heterogeneous and computationally demanding systems that we have in climate science and in fact in many other kinds of disciplines. So, we have multiple paradigms. We've got numerical simulation, probabilistic programming, ML, traditional data analysis, and so on. And then we've got a whole bunch of programming languages in the mix as well. So what can we do in the face of this complexity? Well, I think there are two kind of strategies that we can push on. So the first is to focus on kind of areas where the benefit of automated transparency are likely to be most valuable, and where, on the other hand, the barriers to adoption for new technologies are likely to be lower. So I think there's a clear opportunity there in the kind of science communication quadrant of this diagram, because the applications of computation is simpler, tools and languages are more in flux there, and transparency is actually super important there. But I think we can also go on to this sort of bigger context, but only if we treat the problem of adding transparency into these heterogeneous complex systems as a kind of first-class problem in its own right. And that's going to mean recognizing, for example, that there are other notions of transparency and explainability that are going to need to sit alongside some of the ones I've been talking about, so techniques from explainable AI or data provenance, and then ways of designing sort of interoperability between these notions, ways of trading information for precision in order to get more performance and things like that. So I think the way to proceed is actually to push on these two directions simultaneously. I'm going to talk about the first one a little bit. So the idea of sort of how this can contribute to science communication. So we've already seen how kind of today's sort of scientific outputs are for the most part quite opaque. They're kind of snapshots like this research paper here. We also have things like this visual journalism article from the BBC. It's had some pre-built kind of climate scenarios, but it's not clear what data it's based on, what the underlying science is. And then there are more interactive things like this En-ROADS climate simulator from MIT. So this is quite interactive. I can twiddle these sliders, things change, but it's not clear what the calculations are driving that, what the underlying data is, and so on. So our goal here is to turn our research prototype into a kind of authoring tool for building online apps that are transparently linked to data and are able to kind of explain how they work. So let me drill into a couple of concrete objectives within this science communication strand. So one of them is something we're currently working on. The other one is a bit more ambitious. So suppose let's sort of invert what we were talking about earlier. Suppose we have some input that we care about. There's a particular piece of data that we're looking at in the context of a particular output. So we might be interested in how this output is used. How does it contribute to the output? What other inputs and source code are relevant to us making sense of that input? Well, we can actually answer that kind of question by flipping the kind of related outputs operator that we looked at earlier. So we can ask for our input selection, what is it necessary for? So how is it used, in other words, in all the outputs? And then we can say, what do those outputs demand? And that tells us all the other things that we need to know about in order to make sense of this. So we can think of this as a kind of unit of comprehension, if you like, or a unit of reuse, because we have a kind of closed unit of work in some sense. So I think to make this useful, it's going to need to be combined with other operators for restricting the scope of the query, because a single input might be used in all manner of different ways. And so the answers to these questions can get very big very quickly. But I think with some other tricks, we can kind of get on top of that aspect of it. So I think there's some non-trivial work to do here, but it's mostly UI and engineering work, I think. And then the more ambitious sort of idea within this track of research is what I alluded to earlier. I mentioned intentional transparency. So the idea here would be to take some output feature like the bar we saw earlier, and rather than just giving an account of the needed data, we'll actually be able to produce a standalone computation that reproduces that bar in some sense. It tells you exactly how it's calculated. So these are just mock-ups that I created to sort of give a sense of one possible user interface for this. And there are lots of issues that come up here. There are questions about naming and reference. So we're hoping to borrow some ideas from spreadsheets and notebooks for this. And there's another key observation, which is that if we want these outputs to be intelligible, then I think there needs to be a much smaller gap between the language used to express these solutions and the problem domain. So creating these mockups, I kind of freely help myself to operations like rolling up a lot of dimension, pivoting on the country, and then column-wise operations and so on. But none of these were actually how these examples were implemented. So I think to kind of realize this vision, you have to actually express these solutions in a much more sort of data-centric kind of language that allows you to sort of work very directly with the kind of problem domain. And there's some work of our own that we might be able to draw here on expression problems. So the idea then would be able to implement something like the climate article I showed you earlier, the BBC1, or the En-ROADS climate simulator, but be able to do that in a way that's kind of transparent and self-explanatory rather than just an opaque system. Okay, so finally, let me come back to this larger context I mentioned of the kind of the complex heterogeneous systems where there are multiple paradigms at play, lots of different languages, different kinds of transparency solutions that need to interoperate and scale and so on. Okay, so here's an example of the kind of heterogeneity we get in climate science. So climate models have these pluggable components called parameterizations. You guys will know a lot more about this than I do, but parameterization is a kind of model of a physical process that's below the kind of resolution of the model. So it might be something like eddies in ocean currents or momentum transfer in atmospheric circulation, for example. And neural networks are increasingly used for these components of climate models. So you end up with a kind of hybrid system where you have numerical simulation, you've got your ML, you might have some visualization of the simulation state. And then you might, for example, have some explainable AI technique that Shapley values, and you can use that, let's say, to determine that the network is attending to some feature of the model in order to make a prediction. But then you might be using some other kind of notion of provenance in order to map that information back to the visualizations. It's something like downward slicing that I showed you earlier. And if you've got some configuration in a database or perhaps some observational data, then you might have semi-ring provenance. And so the question is, how do all these notions of explainability and so on fit together? So the kind of questions I think would be good to look at here are questions around compositionality, round tripping, how to combine quantitative methods with some of the symbolic methods I'll be talking about, things like foreign function interfaces for allowing kind of cross-language solutions, and then partial and gradual transparency. So this might mean instrumentation that you can disable in production but keep around for debugging or education. And as I mentioned earlier, kind of trading precision or other information in return for something that goes a lot faster. So I'll just mention one idea relating to this last point, because it seems quite promising. So if we have two dependence graphs that we're using to sort of do this input-output analysis, and they have different internal structure, but they realize the same reachability relation, then they actually induce the same slicing operators. So I think this points to the way to trade intentional information for performance. So you can imagine you've got some big computation represented as a graph. There are some subgraphs that represent an operation that you don't care about, for example. So you might collapse that part of the graph down to some kind of I/O relation that might allow you to scrub at some reasonable speed through the bigger computation. When you get to some bit that you care about, you might then reconstruct a more fine-grained view and sort of thing. At that point, you might want to ask, why did that particular thing happen, rather than just what happened? So, yeah, this seems like an interesting direction to push on to get some more performance and scalability. Okay, so I'm going to stop there. So my conclusion is that the ergonomic goals of open science actually need the computational process itself to be more transparent and self-explanatory. And climate science certainly presents some unique challenges to this idea, but in many ways it's the perfect test bed, because in climate science, more than anywhere else, we want citizens to be engaged, we want governments and policy making to be accountable, we want the science to be super intelligible. And it's not realistic to expect people to do all this work, not because people aren't willing to work in an open and transparent way, but because the kind of pervasive transparency that I'm talking about just isn't something it's really feasible to expect people to do. We need to think of it as a kind of infrastructure problem. So I think with developments in PL, we can potentially make progress towards kind of replacing the sort of opaque snapshots we have today with transparent views of actual computational playgrounds. Okay, so that's me. Thanks a lot for listening. I really appreciate the opportunity for coming and talking to you. I'm going to be very interested in your thoughts.
Okay, yeah, I know.
So, Rolly, thank you so much. I have loads of questions on the semantics and stuff, but we can leave that to an offline conversation. At a high level, you're building a new language, but this is really a vehicle for experimenting with how to map these semantics onto the infrastructure problem that you described there. So the infrastructure problem seems really exciting, right? So what is the next mapping you think would be good for these techniques that's not in an existing language? I guess this is the FFI portion of what you're talking about there.
Yeah, so you mean if we want to sort of, so we've got this kind of sandbox effectively where we can play with the ideas, but without asking the question of how it connects to existing systems. Is that kind of what you're...
Well, if you have the core semantics in my head now, it's basically an FRP monad, which builds a data dependency graph, and then you keep track of the Galois connections through a set of operations, but the computation itself can be is a pure computation based on inputs and outputs, which means that you can have loads of you can run that computation in a VM or in anything else, as long as you can establish those connections between the systems. You can build a distributed programming language that wraps the results of Python scripts and stuff, carefully controls the outputs, or you can do something more fine-grained, depending on what you're aiming for, something in JavaScript or something. I'm just curious what scale at which you think this will be adopted.
Yeah, I think that's still kind of an open question, really. So at the moment, we're definitely focusing on single small program, and I'm thinking about how to make that self-explanatory. I think when you're talking about plugging it into a wider distributed system, there are lots of questions around. I mean, like an obvious one would be, there are sort of things you might have to give up as you go to bigger scales. Like I think, for example, having some nodes in the computation that are able to provide the extension of mapping. So basically, you can be a good player in this kind of ecosystem if you just provide an extensional map between your inputs and outputs. If you're able to provide that as a kind of component, then the larger system that you're part of will still be able to do this end boosting. So I think looking at what the kind of minimum features are that are going to allow an ecosystem to sort of build up like this, like how do you join in with a system like this? What are your obligations as a participant? They're going to stop you breaking compositionality and things like that. Those are the sorts of questions that come up there. But yeah, I don't know how to answer. I don't think the reason
you've actually answered it, but
maybe just a small follow-up question on that. So I'm slightly confused by the complexity of the problem. And so I mean, but what I try to understand is that pretty much like if you expose the full flow of the computation, I mean that would be a way more transparent, right? But on the other side, when I think of kind of like a climate simulation over the next 100 years, where I have pretty much like hourly snapshots of like worldwide state of temperature, whatever, just I guess the storage requirement to actually like keep track of all these snapshots explicitly probably would make at least sending around the data quite difficult, but even storing it, I think I would. Can you actually store that? Is that too much, or? I think that probably is too much. I mean, I think the climate science setting, at least in the kind of time frame that I've been talking about, what it is. I think it's realistically going to be on communicating climate science. It's like, so like there are two ways you can put that climate model. You can think of it as a kind of, a computational simulation in itself with all this kind of content in it. But you could also think of it just as like a data provider, so you could just say, well, here's a load of data that's been generated by a climate model. Yeah. Now I want to do a bunch of data science on top of that. And for that kind of thing, computational complexity is a lot more manageable. So I think those are the kinds of applications we'd be going after, not actually bringing all this into climate models themselves. So that's what I'm like. I mean, I'm really not an expert, but I was just wondering, like, I mean, if I want to do that climate science, maybe ask a question. I want to know, like, how warm is it on Wednesday at noon, on average? I'm not sure, maybe that's a data science question people might ask. But how would I know that I need the data of Wednesday noon rather than Friday afternoon? Right? So in some way, how much do you lose by kind of like pre-selecting the kind of compressed data set that you're in the end allowed to analyze versus kind of, I mean, from my perspective, and maybe that's kind of overly naive, what you actually would want is to have almost like, I mean, the entire computational thing transparently exposed, and then kind of like, I mean, again, maybe like a future work, find a way to have the full access while being scalable in a way. Right? I don't know much about this, and maybe other people do, but I know there's there are kind of techniques for taking snapshots and then reconstructing, rerunning the simulation deterministically.
Just compile the whole thing to Excel. It's got lambdas. It can scale to 50. Most widely used programming language in the world. Right. It's highly optimized for exactly that scenario, right? You look at something a billion columns down the road.
A lot of explanation is difficult here because of the arbitrariness of just fitting neural networks and learn data. And you don't actually learn a model, you just learn distributions and arbitrary sets of neural functions. If you did a PhiML approach, like physics ML approach, then you'd have a model. you have the first principles, but then you can't solve it because it's too hard. So then you use the data to optimize solving the numerical equation, version of the equations. But you have a direct explanation, and you can directly visualize the explanation all the time. So I don't understand why people still pursue these deep learnings. They're not deep at all. Method building models just based on data, and when actually you can write down the equations for fluid flows, or temperature variation, whatever, but you can't actually write that down for the entire ocean and atmosphere and solve it and hope to solve it numerically, unless you do something else like driving the data. But if you can link the two, which is their projects to the Turing, but they did this with Rolls-Royce with jet engine design, and actually figure out where to put more sensors to figure out where there's turbulent flow, and then use those data from those sensors to drive solving numerical equations, actively solving equations numerically. But then you have the model from first principles, and you can do that with lots of systems. In fact, if you do anything with GANs, the generative side has already got some idea of a model usually. So it's like, it seems to me like there's a fundamental thing to shift. The question I was going to ask is about layering of explanations, because your very long-term goal included trying to, I guess you're trying to get the public to get what we're doing. Right? Not only public, the platform omnibus, as they're sometimes called. But there, I would say you need to have some way to generalize abstracting explanations, because the example I would use is from the medical world, where if you go in for some diagnosis and you're given some offer treatment, medics have ways of giving you very simple probabilities of outcomes from treatments, but they're not what the papers say. The medics may not even read the papers, even though once upon a time in the past they may have been able to understand the statistics in the paper about this clinical trial led to these outcomes. But what they'll do is they'll reduce everything, including massively life-threatening conditions, to what's your probability of still being alive 5 years from now if you do this treatment or you don't. Right. Which is a pretty ridiculous reduction, but it's actually understandable. Yeah, and so there's sort of two bits here. It's like how do you help the scientists in climate, especially, automate their simplifications so that they're true and useful, but not too simple.
Yeah, I think that's true. I mean, I kind of imagine that this is a sort of low level of like programming language level explanation that would then have to be supplemented with perhaps more AI based on that language, kind of as one possible tier of abstraction.
Well, I was wondering if you just see common cases that then you can just use useful analogies. So if you find there is lots of, so the example I have is a lot of the public learn to understand exponentials as a result of the COVID pandemic, because they started to see population growth, the number of cases doubling over, some fixed interval, and then a lot of people did suddenly understand something which they normally don't understand. Humans are resistant to understand exponentials, but they got it, and now you can explain it's like chain reactions in climate causing problems because it's just another positive feedback loop, which is bad. It causes exponential. So you actually have a chance, but it's that analogy. We're underlying it, there's some math, and underlying that there's bits of physics, and underlying that. But maybe you could spot common patterns, not using. I'm saying I'm trying to avoid going here anywhere near LLMs or anything like that. But just it could just be really simple that the models you can abstract in the code are broadly similar across these classes, and therefore you can then turn those into analogies, non-false analogies, or all good enough. Yeah. Maybe. Yeah, that'd be very cool.
So following this question, if it still happens on Mondays and Fridays, dynamically executed have the same average temperature at noon, then in your system they would naturally hash cons in, right? Because would they only have a dependency on?
No, that wouldn't be. I mean, that is something we've kind of thought about, but at the moment they would be represented as independent.
Or even though the outputs are equivalent because they have different inputs coming in. But I feel like a bit of a holy grail, because if you do that, then you could slice out common computations in the state of
if you want. So at the moment you talk to that kind of thinking of the dependency graph as an enabling change propagation, but at the moment we are doing that. But if we were to sort of generalize this into something that would allow change propagation, then I think we probably would want to start thinking about memorization and stuff like that, how to share sub-computations when you're doing the updating.
Why would you have a data dependency graph without?
Yeah, sorry.
No apologies.
I'm sure you can talk. Anybody else have questions? People have been quiet so far. Yes, Patrick.
Thank you for the thought. Very relevant. I think it's a lot of our work. I think one question is more just practical in what, you know, if someone wants to try using this today, how easy is it to do that, and how, you know, if we wanted to have, for example, the examples on the website don't have a map like on the world, and we might want to try something like that. Is it easy to extend? Is it using kind of common visualization libraries of the web?
Right. Yeah, that's a good question. So at the moment, it's not that easy. So you basically have to, you know, there's no kind of IDE or support with VS Code plugin or anything, but that's the sort of gap we do want to close next year. With the visualization stuff, we use D3 as the backend, so there's some kind of integration required. So in particular, the selections are something that we kind of is part of our infrastructure. We obviously use standard D3 features to implement it, but it's something that we add to a D3 visualization in order to support it. This kind of particular kind of interaction. So looking at chord pleths or other kinds of mapping graphs is something we definitely want to include, because there's just lots of nice sort of applications in that area.
Anyone? Yeah,
So I think you alluded to this when answering a question over here, but kind of what do you see as the kind of level of complexity in terms of like operations within the code where this is relevant, right? So like that climate simulation, you're not going to go all the way back through that and point towards the inputs that got you to a particular visualization, but your examples do show, you know, I have a visualization. This is being produced based on the outputs of a particular model. Is there some kind of middle ground where it's still relevant, where I can kind of trace back that computation even to pre-analysis, where it's like maybe not as complicated as climate model, but something, you know, in the intermediate, where you could still feasibly produce something that's useful for interpretation?
Yeah, I guess the sort of two issues I suppose that come up are there's the sort of performance aspect, which is kind of important but boring in a way. But the more interesting question is, and maybe this is what you're alluding to, is kind of what happens, you know, as you go back through certain kinds of analysis, the dependencies can kind of explode very quickly. So any kind of aggregation operation, like taking the average or something, that does kind of induce a dependency on a whole bunch of things in one go. So I think we're sort of cognizant of some of these issues and sort of start thinking about them a bit. I think there are some, for the kinds of things you're talking about, where you've got these intermediate, these size programs, I think we would have to make progress on some of those questions. You know, so some of the ideas we've had are, so one thing that you can do is take advantage of the fact that the analysis is kind of monotonic. So if you've got something that you care about, you could sort of create an initial selection that's just like the broad context that you're interested in, and that will reduce this big sort of dependency structure. And then you could focus in, you could sort of add one more thing into your input selection, say, and then you could look at how the demand associated with that changes, because it's going to get slightly larger. And that might be just revealing about the role that one particular actor is making. You know, like it shows you in a sense the additional data that was needed just to support that one additional part of the actor. And that might be a kind of one way to start getting a handle on how to use the same broad approach, but to ask more sort of fine-grained questions that would allow you to sort of look at some of these bigger computations or longer pipelines. So,
Thank you.
Yeah, go.
Maybe you could mention what you and Joe were doing with Marla's paper. Should Marla's paper?
yeah,
I
so
haven't even told her.
yeah, what we were doing there is so this is a kind of Bayesian model averaging sort of example where you've got a bunch of climate models. So this is an example where you're really treating the output of the climate model as a data source. You don't care about the fact that it might take a month to run sort of supercomputer or whatever. But what you've got is a bunch of simulations of different climate models, and you're trying to do some kind of weighting. You want to assign a weighting to each so that you can come up with some kind of aggregate sort of based on your assessment of how reliable each model is. And so one of the things you need to do in that kind of setting is you've got your different models generating a time series, and they may not kind of align exactly, because there could be like a phenomenon that occurs in one of the simulations, like a weather event. But because you're interested in the kind of macroscopic behavior of the system, if that weather event occurs at a slightly earlier point in the time slice in another simulation, you don't want to fail to align those events. You want to sort of treat them as the same event. So you have to do this kind of assignment across the time series of how you're going to map up. So I think it's a permutation that you're trying to generate. So you don't, assign anything twice. You sort of give every element in one time series, and you need a partner in the other time series. So there are various existing techniques for this, and the paper Dominic mentioned was developing a new technique. And for us, it was an example where we could show this kind of linked inputs operator that I mentioned at the end. So, you could imagine making a selection on one of the inputs in one of the time series. And what it's going to show you, the analysis, is all the other points in the other time series that were considered as kind of candidates for being associated with the point you initially selected. So it would give you some kind of insight, even just in a purely extensional view of things. So without any view of the internals of the algorithm, in other words, but it would still reveal something about what was relevant in creating the, when the algorithm decided to correspond those 2 points, what points were actually taken into account. So I guess that could be an example of a sort of medium-sized problem potentially. In fact, it turned out to be a bit too big for us because the complexity of the kind of assignment algorithm itself was large, so it didn't make for a good example for us.
Still, I felt like you were getting, relatively close. And Joe had. So this is Marla Verdi's paper about the likely time invariant weighted model average paper from here. And Joe had covered quite a lot of it into it, which I was like, oh, it's pretty cool. It's getting there. It's starting to show that. Trying on a bit more.
Where did it seem first? Was just memory explosion or something?
No, because we're looking for examples that we can put to a paper and use to illustrate this idea of linked inputs. And the problem is that just explaining the algorithm is already like a kind of 2-page proposition. So I think we want to come back to, we've still got it in our code base as an example. We want to use it down the line.
I mean, it didn't seem like you were far off having a whole, you had most of Marla's.
Well, we actually used a different algorithm. So there are
different algorithms, but it was sort of, it wasn't an order of magnitude. No.
So maybe I can ask, I had a question about pragmatics on this, right? Let's say you showed us in the beginning a paper from Nature or something showing some graphs. And then let's say I'm the author of that paper and I want to make it useful. So now I'm going to submit some code somewhere, or maybe I'm going to host it, which allows people to create a website that says go click on this, you'll see the data values that correspond to it. So now I have to open up all the data, right? Now, what happens if I change the algorithm because I found a bug in it? So now I have to version the data because the data may change, and the data may have privacy issues, and then I'm going to have the code versions. So, how pragmatically do I tell my grad students version the code, and if you improve it, then when somebody clicks on it, you can show the latest version, the version that was used to generate the paper. In other words, what you are really doing is that the paper becomes not a static fixed bit of paper, but something that is malleable and needs to be checked. When we're running into this in space, but we have this one data point called equivalent permanence. To get that point, we have probably like a couple of billion data points behind it. Right? All sorts of stuff, randomized stuff going on. If you run the algorithm, the data points will change because we randomize internally. So I was just thinking about if we publish this, we're trying to publish this, we want to make it transparent and open. I don't understand how you, okay, so there's 2 questions. One is how do you make it a checkpoint? And the second thing is how do you do cascading? Because we depend on other papers, right? So I need them to publish their stuff. And so that, so one point can depend on 100 points in my paper, will depend on 10,000 points in 100 papers.
Yeah, I mean, that's a good point. That's an issue that would exist. Isn't it?
Yeah.
Obviously, we don't identify any problem, but I guess with this kind of infrastructure, I think actually any of the stuff that you tell me about sharpens and that sort of, I think this is way outside of the scope of this project, but I guess it's interesting to think about what other kind of infrastructure would need to be around it in order to support the kind of thing we're talking about. But I'm thinking of, sort of persistent URLs for data that's versioned, so that if the data changes, then it's a new piece of data. And it may be partially shared, it may share some representation with the previous version or whatever, that sort of technicality perhaps. But, you know, that's an issue that the sort of data science community already has, like how do we deal with version data, things that are changing, and reproducibility in the context of big complicated pieces of research that we're using results from other papers and so on. So we don't have any more of a solution to that than it is today, but I think it's clearly an important question. You know, because to make it on the kind of long-term vision, there would have to be progress on some of those questions as well.
We like to have simple explanations of what's wrong with some things. I remember writing a paper to Nature, a letter to Nature, because somebody published they published a paper which said this is these graphs show you that people are reacting to congestion in the UK, US internet links. And we looked at the data, and it was obvious that they trusted nighttime, and there were no users at that point, so it was obviously wrong. You could just look at literally the timestamp. So they were in California, and they were not understanding because it was nighttime. There was nobody using the thing. I mean, you know, but you know, traffic. But you know, so there was an explanation which the graph didn't show. That would be useful. And in climate, well, actually, I think in public trust of things, if you show honesty and transparency about when things are right, you increase trust in the long run. Not the same as always being uncertain. It's really hard to get people.
Let's end with the last question and back over.
It's kind of two rolled into one. One is like, I think a lot of the way you would think about using these visualizations in some and in papers is in like some kind of narrative. And often within that narrative, there's actually a lot of references back to the data itself. Right. Have you thought about again, like embedding fluid or these things into something that's easy to write narratives that link back to the data? And then on top of that, I think that helps a lot with accessibility. And even from your demos with the graphs, you know, you can actually start getting numbers which might be easier to have, you know, like kind of voiceovers for numbers rather than trying to explain visualizations. So it's part of the things for accessibility.
Yeah, no, that's a super interesting idea. So I guess what I vaguely imagine, not, you know, having the resources to really spend time with it at the moment is some kind of maybe like a markdown type set up like Porto or something, where you can sort of escape to a bit of fluid code, and you could obviously do it with the visualizations that you've shown here, but also any kind of computed value that you want to add into the paper. So it doesn't have to be just visual. We're focused on those just because they're nice and they're easy to sort of get a sense of. But you know, anytime you write a paper and you put a number in it, and you're quoting your own results in some way, then you want exactly that same sort of traceability to be there. So that's, yeah, I think it's a really good thing to be focusing on. Thank you.
Okay, that brings us to time. Thank you very much, Ravi.